An early-stage coverage measurement methodology for common features of a system-on-chip verification using design metadata, and the large language models. Abstract. This paper introduces another coverage methodology termed Common Task Coverage (TCT) for assessing the coverage of the common features and intellectual properties (IPs) in the simulation-based verification of a system-on-chip (SOC) design. The approach introduces the common tasks (CTs) to assist users in verifying common features effectively, to enable early-stage coverage application and overcome the limitation of the conventional schemes, which are typically constrained to a post-simulation and measurement. We define coverage beans as IPs derived from the design metadata. This allows for a quantitative measurement of the coverage within the verification plan and the universal verification methodology testbench (UVM-TB), utilizing the large language model (LLM), and we also developed an in-house dashboard to monitor the status of overall coverage. The proposed coverage schemes reduced the turnaround time (TAT) required for reviewing the verification plans to identify the coverage gaps in cities, and facilitated the quantitative assessment of the cities and UVM test bench, and ultimately enhances the systematic verification quality of common features and IPs from the early stage of the design verification. Chapter 1, Introduction. The complexity of the modern SOC designs has been continuously increasing, leading to a greater demand for resources in SOC development, as well as the escalated complexity in and the demands on SOC design verification. The SOC has become a critical bottleneck in the development process, requiring the advanced methodologies and tools to ensure the correctness, reliability, and performance of these intricate systems. Typically, SOC designs are not developed from the scratch. Instead, they involve the integration of the pre-qualified the intellectual properties or the subsystems, which are either independently developed or provided by external vendors. These IPs are generally presumed to be error-free based on a thorough verification conducted during their development phase. Thus, the primary focus of SOC level verification is checked to the integration between the various design components. SOC-DV employs various methods, including UVM, Universal Verification Methodology, based dynamic simulation, and static verification. Structural properties such as class and reset are effectively verified using the complementary techniques like CDC, clock domain crossing, and RDC, reset domain crossing. However, functional simulations remained essential to ensure the proper operation of these features with the tightly integrated system-level behavior of the SOC. This paper focuses on a UVM-based functional verification to assess the functionality of the common features and IPs, which is facilitated through the use of the common tasks (CTs). The term common in this paper refers to features or functions that are shared across various blocks within the SOC. So to verify that these common features in each block, such as clock, reset, security, and power, as well as the common IPs such as Clock Management Unit (CMU) and Power Management Unit (PMU) in SOC. A set of the tasks has been defined. These tasks constitute over 40% of the total UVM-based verification effort and are primarily dedicated to the functional verification. Each verification specialist implements a standardized function scenario in UVM and release them, providing a guide to assist users and verifying common features and IPs with greater convenience. In other words, implementing CTs in the SOC-DV ensures that its common features are functionality verified. These are two significant challenges in the current coverage schemes with respect to city. So the first, conventional coverage schemes can only be applicable after simulation, and linking their use to the very late stages of verification. This delays the application increases the risk of the undetected logic or functional flaws, which is leading the cause of the bugs in application-specific integrated circuit (AC). This means if a city for an IP is inadvertently omitted in a verification planning step, and issues are detected in a later stage in logic development, substantial resources may be required to resolve the problem. Moreover, due to the large number of the SOC function scenarios and the inherent complexity, implementing a functional coverage scheme can be highly complex and challenging. Even certain coverage targets, such as power and clock scenarios, are not effectively measurable through code coverage metric. In this paper, we introduce Common Task Coverage (CTC), a novel methodology designed to enhance the functional verification of SOC designs by measuring the coverage of common features and IPs. By defining coverage beans based on design metadata and employing the LLM, CTC enables early-stage quantitative coverage assessment within the verification plans and UVM test benches, as shown in Figure 1. This approach reduces the turnaround time (TAT) for identifying coverage gaps, facilitates comprehensive verification, and improves the quality of verification for common features and IPs from the initial stages of the design. Figure 1 is the CTC methodology using conventional simulation-based verification process. Chapter 2, Common Tasks in SOC Design Verification. In SOC-DB, cities are defined to facilitate the implementation of scenarios for common features and IPs in UVM. Due to the inherent complexity and scale of SOC, fully applying the constraint random verification method, which is commonly used in IP-level DB, proves challenging at the system SOC level. Consequently, directed test scenarios that capture the core features are established alongside constraint random scenarios to ensure the comprehensive coverage. The main objective of these cities is to verify the functionality of each IP within a variety of shared scenarios, ensuring the compatibility and correct operation. Expert DB engineers are assigned to each common feature or IP, providing UVM sequences and checkers for user convenience. As shown in Figure 1, cities are defined during the design specification review phase and implemented during the simulation-based verification step. To classify the cities, features, and sub-features, feature and sub-feature categories are established. Here, the sub-features represent specific features of the IPs of the SOC, sub-features represent the specific features and or IPs of the SOC that are commonly require verification in each block and IP, while features serve as groups of these sub-features. Typical examples of the cities within the SOC-DB are represented in Table 1. Table 1. Typical examples of common tasks in SOC-DB. For example, if a DB IP resides within the block that supports clock gating controlled by software, UVM pseudocode can be implemented as illustrated in Figure 2. By invoking the clock gating CT within the IP's function scenario, it can be confirmed that clock gating logic, including multiplexer, MUX, and gates, is correctly integrated with the SOC, and the IP can operate as expected following software-controlled clock gating. So, the Figure 2 is a typical pseudocode implementation of a clock gating controlled by SW for DMA. So now the chapter 3, common task coverage measurement methodology. The overall coverage scheme is achieved through the three-step measurement approach. First, to define the scope for coverage beans, we leverage the metadata of the design specification as the primary objective of simulation-based verification is to validate the designs in accordance with their specifications. Second, to mitigate the risk of the missing scenarios in the verification planning phase, whether due to inadvertent user errors or design modification during the register transfer level RTR updates, we establish the coverage beans based on the scenarios defined in the verification plan, which constitute an early stage in verification processes. This allows for effective implementation of CTC within the verification plan itself. Third, to evaluate whether the CTs are appropriately defined within the UVM-TB. Given the responsibility of the leading CTC and integrating into the TB falls to the distinct teams, we introduced the use of the LLM to facilitate precise measurement of the TB implementation coverage. Ultimately, these coverage measurement methodologies are migrated within the in-house coverage dashboard, enabling DB engineers to monitor the status of the CTC and conduct through the reviews of the achievement comprehensive coverage closure. The architecture of the overall system is illustrated in Figure 3. Figure 3, overall architecture for the CTC. A. Define coverage being based on the design metadata. The foundational step in implementing coverage is defined coverage beans. 4 distinct specifications are selected to drive the metadata to create a coverage bean for CTs are illustrated in Table 2. IP names within each block are gathered from the register map, while master names obtained from the network on chip and OC specification. Power features corresponding to each block are sourced from power specifications. Additionally, to address the specific conditions that require verification from the SOC implementation, IP-XACT is also employed. Table 2. Design specification and contents from them to generative metadata. And we implemented CT functions to generate the CT coverage beans using metadata from the design specifications, with details outlined in content for design specification for metadata in Table 2. The process steps are depicted in Figure 3. So the core IPs defined in this methodology are targeted with the distinct functions. They are identified by excluding common IPs covered by CTs using register map and NOC specifications. So the functions are defined to create CTC beans for each IP within each block, utilizing inputs from the common IPs and metadata from the specifications and IP-XACT. So the additionally CTC beans are generated for each RTL level to track the design changes. As an example, as illustrated in Figure 4 and A and the pseudocode for Figures 4b, when considering the features clock and sub-features clock gating by software. Since the common IPs in the block A include the CMU-A, and the CT functions can be core IPs invoked, which returns the IPs CPU-A and DMA-A in the CTC bean. Figure 4 is A SOC example. B. The operation of CT functions in the process of generating CTC beans from the SOC in the pseudocode. We identify the test scenarios involving the CTs for IPs often overlooked during the verification planning step, resulting in the emergency of the bug after RTL freeze. To mitigate such issues, we implemented a coverage measurement systems for the verification plan in the verification plan. Each CT is categorized in pairs with its corresponding features and subfeatures, with the associated IPs listed for each CT. So our in-house dashboard in equipment with the application programming interface API to retrieve the coverage beans data and comparing with the verification plan. After CT pair along with its respective features, subfeatures and IP is found to match exactly with the data from the verification plan, the status is recorded as covered. Conversely, if mismatches or omission are detected, the status is marked as not covered, requiring users to provide reasons in the notes section to write the reasons why it is not covered section, and update the status to waived as necessary. For instance, in Figure 5, to do the absence of the clock gating by a software or CPU-A in the verification plan, the status recorded as not covered. Figure 5 is an example of the verification plan coverage by coverage dashboard API. Second B is coverage measurement for UVM-TV using LLM. To enhance the verification is ensuring thorough coverage with integrated CTC for UVM-TV using the LLM. Since different teams may handle the creation and application for these tasks, and inconsistency in implemented by the DB engineers by possible. Even if the detailed guide for the CTS and the test sequences are provided, a user integrated with them may inadvertently cause users, potentially leading to detect. Thus, we employed an LLM to evaluate the implementation coverage of the UVM-TV. By automating the analysis of the UVM-TV code, the LLM can identify the structure and the logical patterns, verify the alignment within the UVM best practice, and swiftly detect the syntax error, misuse the functions, or incorrect sequence configuration. This offers a significant advantage over manual code review by reducing time and improving accuracy. To protect sensitive and confidential data, such as the design specification, RTL, and the UVM-TV, we chose to develop the local LLM based on an open source model rather than relying on external network models like ChatGPT. And since languages relevant to our work, such as Verilog and UVM, are underrepresented in open source models, we selected the DeepSeek-Coder-V2 model, known as its high benchmark scores and specification training Verilog and system Verilog. We fine-tuned the LLM for this specific application. We trained it on project-based data, including the verification plan, RTL, UVM-TV, and the hardware description document to HDD. And additionally, we employed retriever augmented generation (RAG) to allow the model to reference in-house data for query, such as verification plans, RTL, and UVM-TV and HDD. The RAG addresses inherent limitation in LLM by retrieving relevant external example information, thus filling the knowledge gaps into improving the contextual accuracy. To following steps outline our development of the fine-tuned LLM and our approach to measuring city implementation coverage in UVM-TV as illustrated in Figure 6. Figure 6 is a pipeline for coverage measurement in UVM-TV and the implementation of log-based prompt. Step 1. Fine-tuning the LLM. The DeepSeek-Coder-V2 LLM-based model is trained in RTL, TV, and verification plan to improve each comprehension. This step is essential, as the base model understanding of the proprietary in-house data is insufficient due to the initial training on openly accessible data alone. Step 2. Embedding the verification plan as a code with a fine-tuned LLM. We generated a vector database for pairs of verification plans and test code derived from the UVM_test using the fine-tuned LLM from the step 1 and stored these faced and AI similarity search FAISS system. As open source embedding models are generally trained in wider spoken language like English and Chinese and Korean, their comprehension appropriately can be delimited. Thus, employed our fine-tuned LLM to create this vector DB, enabling improved similarity assessment. Step 3. Embedding test codes and sequences with fine-tuned LLM. We similarly generated vector DB for pairs of test code derived from the UVM test and sequences derived from the UVM sequence, achieving them in a FAISS for the further analysis. By generating the vector DBs separated from step 2 and 3, the diversity of similarity assessment is enhanced, leading to the development of the more precise vector DB. The step 4 is preparing the prompt input of the phase for a RAG. To leverage the RAG concept in the prompt, we apply the phase to vector DBs from step 2 and 3, as well as a vector DB of the verification plan created a fine-tuning LLM. Through his approach, we could provide the LLM with comprehensive contextual data, including verification plans and test commands and matching sequences, enriching the prompt with relevant in-house data. Step 5. Implemented RAG-enhanced prompt. Using RAG as input, the fine-tuned LLM, we developed a structure and prompt containing test commands, sequences, and CT guide that are released by each DB specialist. The prompt instruction the LLM to test files. According to the provided CT guide, as described in Table 3, in particular, the CT guide includes an overview of the CT, implementation, instruction, and sample code. To further improve responses accuracy, we incorporated the chain of thought technique, which requires models to generate step-by-step explanations rather than predicting answers directly. COT helps the LLM in systematically accessing whether commands, tasks, and sequences align with each step of the guide, ultimately enhancing verification precision. Table 3 is content in Common Task Guide. Section C, in-house coverage dashboard for coverage closure. We developed an in-house coverage dashboard that integrates key metrics and functionalities to facilitate efficient verification coverage for both verification plan and TB implementation, while also monitoring coverage data in real time to provide a continuous update on the overall status of CTC. Utilize Apache Airflow, an open-source platform for workload scheduling and monitoring. CTC bins are synchronized with the latest data and periodically stored in DB. The systematic includes coverage visualization tools when heat maps for assessing block level coverage. Details coverage status report and mechanism for user review waivers. The dashboard is seamlessly integrated with verification plans and TBs, providing comparative analysis and feedback to ensuring alignment with the verification objectives. The web-based user interface UI is developed using a Vue.js, an open-source JavaScript framework as illustrated in Figure 7. By centralizing coverage monitor, this tool enhances the efficiency and effectiveness of the verification process, so ultimately contributing to optimize coverage closure. Chapter Figure 7 is in-house CTC dashboard and its heat map. And chapter 4, chapter 9, chapter 4, right. Chapter 4 is the result. The A, coverage measurement result for verification plan. The result demonstrates effectiveness of CTC methodology in identifying verification gaps across projects of verifying sizes. In Project 8, which involves a large SOC design, 293 gaps were identified out of the 10,641 beans, resulting in a 2.75% gap rate. Conversely, Project B, a smaller SOC design, 216 gaps were found in 4,325 beans, yielding a higher gap, the gap rate of the 4.99%. The analysis revealed the omissions due to the oversight were the dominant cause of the gaps, accounting for 58.36% in Project A and increasing significantly to 96.30% in Project B. gaps related to the introduction of the new IPs or features were more prevalent in Project A, 39.93%, compared to Project B, 1.85%, reflecting the greater complexity of larger designs. These results highlight the methodology's robustness in detecting gaps across diverse causes and its adaptability to SOC projects of different scale. That is Table 4. Coverage gaps identified through the coverage measurement for the verification plan. Section B is coverage measurement result for a TV implementing using LLM. Figure 8 illustrates examples of the fine-tuned LLM that were retrained using test sequences and verification plan and a log-based prompt. The figure presents the two test items from the verification plan for a specific city, as where the left example shows the result of yes, indicating covered, and the right example shows no, indicating not covered. Detailed exploration and reasoning are provided with the code as indicated by the final result highlighted in the blue in Figure 8. The printed message from both examples demonstrate that the fine-tuning LLM comprehends system value as well as the variety of the proprietary data used in the training. By leveraging the RAG and in the COT tests, the model enhances result accuracy, making decisions step by step with thorough logic and reasoning. Figure 8. Examples of fine-tuned LLM determining the UVM-TV coverage guided by city. To evaluate the performance of our methodology, we have chosen to use a confusion matrix as it is an effective benchmark for assessing the accuracy of classification models and is well suited for evaluating coverage outcomes. This model provides insight into how accurately the methodology predicts actual outcomes by comparing predicted classification to true classifications. While benchmarks like General Language Understanding Evaluation, GLUE, and multitask language benchmark, MTBench, are commonly used to evaluate LLM performance. They are unsuitable for a fine-tuned LLM in CTC methodology. This is because CTC measure coverage in binary terms. It's covered or not covered. So, as shown in Table 5, the model achieved an accuracy of 0.94, indicating that the 49% of all predictions made were correct. The precision was 0.89, demonstrating that 89% of the positive predictions were accurate, highlighting the model's reliability in minimizing false positives. The record was notably high at 0.98, signifying the models successfully identified 98% of all actual positive cases, indicating strong sensitivity. The effort score, a balanced measure combining precision and recall, was 0.98, underscoring the model's effectiveness in maintaining both accuracy and comprehensiveness. These results illustrate that our fine-tuned LLM performed with exceptional precision and recall, achieving robust overall classification capabilities. Table 5. Confusion matrix and evaluation matrix for the fine-tuned LLM in a specific project. Age confusion matrix, BG evaluation matrix. So to evaluate the significance of the sections within the CT guide, we conducted 6 experiments under different conditions as outlined in Table 3. The corresponding metric results are presented in Figure 9. So each experiment either excluded a specific section or included only one section in the guide. The result indicates that providing more detailed content in the guide leads to a higher metric scores, demonstrating the coverage model perform more effectively when all sections are properly implemented, as shown in the figure and shown in the case 6, which represented the optimal scenarios. When only the test implementation section was included, the scores were low listing, although the all metric remained above 0.65. This suggests that a well-implemented test implementation section is essential. Furthermore, omitting the design overview and example code scenarios, cases 4 and 5 result in accuracy reduction exceeding 0.1 points, highlighting their importance. Interestingly, the score in case 3 remained incompatible to that in case 6, suggesting that scope information can potentially be assumed from other sections. In conclusion, a more detailed city guide enhances LLM understanding of the cities and leading to a more accurate coverage result. Previously, manual verification reviews conducted by project managers and DV engineers required a minimum of 7 days due to the complexity of managing multiple IPs within the SOC. These reviews often resulted in overlooked test cases and missed coverage scenarios due to the human limitations. With the implementation of the CTC methodology, the review process takes only 1 to 2 days or less. Figure 9 is a comparison of 6 experimental cases for each evaluation metric. Conclusion. We introduced the CTC methodology designed to enhance the quality of the functional verification for SOC designs by measuring the coverage of common features and IPs. By defining coverage bins based on the metadata and leveraging LLM, and CTC enables early stage and quantitative coverage assessment with the verification plan and the UVM-TBs. This approach significantly reduces the TAT for reviewing the verification plans, allowing for the identification of the coverage gaps in cities and facilitating the comprehensive semantic verification from the initial stage of SOCDV. The fine-tuned LLM demonstrated the robust capability in accurately predicting the coverage of UVM-TB implementation for cities, thereby improving the reliability of the verification process and enabling the early identification of potential coverage gaps. The granularity of the coverage API in our approach provides flexibility beyond the standard system value coverage API, empowering users to define and generate coverage bins directly from metadata. This minimizes the need for extensive involvement from the EDA partners while maintaining the precise control over the coverage definition and measurements. Additionally, the methodology supports real-time updates and feedback through an integrated in-house dashboard, further enhancing the verification quality and efficiency. The CTC methodology is highly scalable and can be easily applied across diverse SOC verification applications, and it can be implemented immediately using design metadata. These capabilities position the CTC methodology as a robust and efficient solution for advancing SOCDB. The CTC methodology has certain limitations, including its reliance on the quality and completeness of the design, metadata, and its primary focus on simulation-based verification, with a limited integration of static verification techniques like CTC and RDC. Additional LLM performance may vary in handling complex SOC designs. For the future, our future work will aim to enhance the LLM adaptability for diverse architecture, integrated static verification method into a CTC framework, and improving automation in design metadata extraction. This effort will strengthen CTC's scalability, reliability, and effectiveness of an SOCDB. There are 8 references. Okay, today I read this paper an early stage coverage measurement methodology for common features of system-on-chip verification using design metadata and large language models from DVCON2025. Thank you for your time. See you next time.